Okay, morning. Let's have the last lecture. Okay, so we only need to go over a couple examples on Stokes Theorem, and that'll be it. Okay. Okay, so in the last lecture we covered two important theorems. One is divergence theorem, and the other is Stokes theorem. As I said, these two theorems basically made use of everything that we learned in this class. According to the Stokes theorem, what it says is, okay, let surface S be a smooth surface bounded by a smooth curve C. Then, calculating the circulation or calculating the line integral around the closed curve C is equivalent to calculate a surface integral, which is here, right? So the surface integral here, basically integrating is the circulation. It's a curl, right? This is a curl right here. And the important thing is, okay, you need to orient the surface S and C compatibly. Okay? So by this means the direction of the C and orientation of the S, which is represented by the n hat, the unit normal vector, okay, they need to satisfy the right-hand rule. Okay? Yeah. So basically, the question gives you the direction of the C, then you have to pick a proper n hat based on right-hand rule. Okay? Yeah. So for example, the C right now is picked as a counterclockwise looking from the top. Then according to right-hand rule, okay, the n hat direction for the S, okay, any S that is bounded by the C, and this basically is pointing out right here. Okay, yeah. So there are two different ways of the right-hand rule, as I showed you in the last lecture. One is to use your thumb pointing to the direction of the C. Use the index finger pointing to the tangent to the surface S. Now, tangent to the surface S, basically tangent to where the S is. I mean, there's no surface S at the bottom, so your finger doesn't tangent to the bottom surface, right? There's nothing there, so only tangent to there, and then the middle finger points to the n hat direction, right? Yeah. So that tells you you have a pointing up n hat. Otherwise, you have another way is you draw a little circle around certain location, okay? And for the circulation of the circle here, okay, it needs to be satisfying the right-hand rule. In this particular case, so the direction of the circulation, okay, is this direction. So this direction and this direction, okay, they are parallel to each other. And then use your right-hand rule. The thumb is the n hat direction. Okay, yeah. So pick the n hat properly, because if you have 50-50 chance anyway, so if you pick it wrong, you get a negative sign basically, right? Yeah. But technically that's all wrong. Yeah. Okay. So let's take a look at okay, an example right here. So let's look at a simple example first. So here's a vector field, and we have a circle. We have a curve C, which is a circle. Okay. So suppose that we orient this curve C counterclockwise, okay, from the top. Okay, so here's a curve C here, circle. Okay, there we go. So that's the circle. Okay, and now what we want is we want to calculate the line integral, okay, around the curve C. and but we're not going to calculate line integral. Okay, so if the question asks you is calculate line integrals, and then you can. This is actually not bad. It's just to parameterize the curved circle and then calculate line integral as it is, right? But let's say in this question here, we're going to calculate the line integral using Stokes Theorem. Okay. Okay. So now using Stokes Theorem, basically we're going to focus on this side here, right? Focus on this side. So the number one question, focusing on this side here, you need a surface to calculate this double integral. Okay? But in this question here, it didn't specify any surface for you. So as a matter of fact, if you look at the Stokes Theorem, as we were talking about in the last lecture, this is actually surface independence, right? So because giving a smooth closed curve C, you can have an infinite number of surfaces enclosed by this surface by the curve C. Okay, so for example, you can have a surface right here. You can have any surface here, but there is one very simple surface in this particular case, which is what? Basically the circle, right? So it's the disk enclosed by this circle here. Okay, so the disk right now is in the xy plane. Okay, so you can, in order to simplify the situation here, let's say we're going to pick the S as the disk in xy plane. Okay, so here you have the freedom to choose the S here. Okay, but maybe in the question that I gave it to you, I will specifically say what kind of surface. Let's say here's a surface. For example, maybe the surface is this. Maybe the surface here's the surface. Here's the surface is this way. Here's the surface. It's a cone here, right? Inverted cone here, or maybe the other way. Okay, so this is the cone here, and I want you to calculate this line integral, okay, using Stokes Theorem, and where the surface, okay, is that cone bounded by the curve C. Okay, so in that particular case, if I specifically say in the question, then you choose the cone. Okay, so if you don't choose the cone, you go ahead and use the disk, you calculate it, you get the right answer, but you will get a certain point deducted. Right? Is that clear? Okay, good. So in this question, let's pick the disk here. Okay, yeah. Looking at the formula here, we need to calculate the curl. Okay, so first calculate this del cross F here. Yeah. Here's F right here. So calculating curl, the formula is the determinant. So now you have the formula now. This is 2y, 3x, negative z squared. Okay. So now you have the formula. Now you can look at the formulas. You don't have to memorize now, and you will get, this is basically k hat. Okay, so it's quite simple, k hat. Okay. Okay. So k hat, and then come back to this double integral, and we need this n hat dA at here, right, for the calculation. So what's my surface? My surface is this disk at here in the xy plane. So in the xy plane, then there comes the question now. What direction shall I pick for the n hat? Because there are two directions, right? Yeah. So right-hand rule needs to be satisfied between this orientation of the SC and orientation of the n hat. So C is going counterclockwise. So the n hat must be pointing up. Okay, it must be pointing up. So right-hand rule, right? Yeah. So which means the n hat here is basically the k hat, right? The k hat. Okay. And the other thing is, what we're dealing with the surface, right? So basically, remember this is a surface integral. Okay, this is basically a surface integral. When you deal with surface integral, just bear in mind we're going to do review. There are couple different cases. There's this spherical surface, cylindrical surface, a surface parallel to a plane, or it's an explicit kind of surface z equal to f of xy. And in this case here, this is basically a surface in the xy plane, which is parallel to the xy plane, right? So that dA basically is a dx dy. Okay, yeah. So n hat is k hat, and dA essentially is dx dy. Okay, but you will see that actually in this case we don't even need that. So now I'm gonna plug everything. Okay. So this line integral equal to this surface integral. The key hat is 0, 0, 1. Dot what? Dot n hat dA. N hat is another 0, 0, 1. dA, dx, dy. Okay, so which is s dx dy, right? Yeah. So that's pretty simple. And you don't really need to do any further calculation using considering Cartesian coordinates, which is basically this one give you the area of the surface S, right? And this surface S is the disk, so it's basically the area of the circle. So that's pi r square, and circle is radius of 3, so that's what, 9 pi, right? Yeah. Okay. So this is general. Now, if this is not 1 at here, if this is not 1, if there's something at here, let's say if there's maybe x squared or plus something here, right? So then the next step what you do is basically this is a double integral. Double integral over a region of S, which is a disk in the xy plane. So you probably would choose polar coordinates, right? Transform those x and y into r and theta, right? Okay, and then find the limits for the r and theta, then do this double integral. Okay, yeah. So that's the this question right here. Okay. Any questions? All good? Okay. Yeah, that's it.
How do you find the n if you close the cone?
How do I find the n here?
If you close the cone?
If it's what? Oh, it is a cone here. Well, same thing. Right-hand rule, right? Right-hand rule first for. If it's a cone at here, then you have to look at right-hand rule here. Let's say right-hand rule. First thing is thumb goes to the direction of the curve, and index finger points up. Okay, tangent to the cone, and then middle finger is the n hat. So in this case, I guess my n hat will be pointing up like this, right? Yeah.
What would be the value?
Oh, that depends on the cone function here, right? Depends on the cone here. Okay. Yeah. So in particular, usually what we see the cone, right? Yeah. This is an inverted cone here. But in our lecture, usually we're talking in the lecture here. This kind of cone here means 45 degrees, z equal to x squared plus y squared, right? Yeah. So if you were invert it, put a negative sign, and then shift it a little bit. So anyway, that could be figured out later. Okay? Yeah. But once you have the cone equation, you need the n hat, right? And this is a explicit. This is an explicit surface, and you have n hat dA, basically n hat dA equal to negative fx negative fy 1 dx dy. Okay. As a matter of fact, I think in the next example you'll see that. Okay. Yeah. So let's look at this one here. Y, x, z, and x squared. Okay, so here's a vector field, and now we're gonna. This example is the last year exam. Okay, the last question in the last year exam. So, and you're not gonna get this one anymore in this year. You get different ones. Okay. Here is the C here. Okay, so here's a curve C. Basically, it's a curve C has 3 segments here, okay? And it's going this way, okay? And connecting these points 1, 1, and here, okay? So what we need is we need to calculate the line integral of this curve C, okay? But we're not going to calculate line integral. If you really need to calculate line integral, then you have to calculate over this curve, that curve, this curve, right? 3 segments. Okay. Yeah. And we're going to calculate using surface integral, Stokes Theorem. Okay. Yeah. Number 1. Okay. Calculate this curl here. Okay. So same thing. So this is f at here. Okay, plug into the formula. okay, you're going to get negative x, negative 2x, and z minus 1, right? Yeah. So this step is important. This step you have to get it right. If you get this step wrong, basically the surface integral won't be right? Okay. So be careful with that cross product. Okay. So then the next thing is about this n hat dA. Okay. Again, this question didn't specify a surface S for you, right? It didn't specify what surface S you should calculate this double integral, which is bounded by the curve C. So I guess one easy choice for us to make use of, which is basically what? This triangle here, right? This triangle, okay? Yeah. So if I use this triangle here, then I need to pick basically. You need to know what this surface S is, right? And I need to pick the right direction for the n hat. So right-hand rule, right? Right-hand rule. Use either right-hand rule. If I use this little circle right here, okay, and this right-hand rule, so the n hat must be pointing this way, right? It's pointing this way. Okay. Okay. So. The next thing is I need to figure out what the n hat dA is, or n hat is. So this is a plane, or this is basically a plane here. So, but we need to figure out the plane equation, and this is basically back to the beginning of the course now. So how do I figure out a plane equation? You can figure out the plane equation based on the coordinates, right? Yeah. You can construct two vectors, okay? Then find the cross product of the two vector, which is basically the n direction, then use the plane equation to find the plane. Okay. But the other way is, I think we have done quite a few exercises. You can actually figure out the plane equation quite easily, because this is 1, 1, 1 all at here, right? So this line here is x plus y equal to 1, and this is xy as a xz. So this line here, right, is x plus z equal to 1. And this line here is z plus y equal to 1. Okay? Yeah. So the three lines are basically intersection of the plane with the three sides of the wall. And actually the plane basically is x plus y plus z equal to 1. Okay? Yeah. Right? So if you, for example, the line at here basically set z equal to 0, you get that line. For this one here, you set y equal to 0, you get this one. You set x equal to 0, you get this one. Okay? Yeah. Okay, so here's a plane here, right? This is a plane, or this is a surface we're conducting the surface integral. And then you quickly go into those different cases of the surface integral now, right? So which case that we should use in terms of this surface at here? This is not a spherical, this is not a cylindrical, and this is not parallel to any of this side of the wall there. So this has to be what? Right? It's got to be a explicit surface at here. Okay? Yeah. So in this particular case, right? Here is the explicit surface z equal to f of xy. And what is f of xy? 1 minus x minus y. Okay? Yeah. So then we're back to this formula for the n hat dA for an explicit surface. If you look at your formula on the second page, actually on the first page. On the first page at the bottom, to the second line from the bottom, okay, there's a general surface explicit. The n hat dA equal to positive, negative, negative fx, negative y 1 dx dA. Anybody doesn't have the formula? Okay, so if you look at the formula, right? You have a positive, negative, but we figure out that the n hat is pointing. There's an up component, so we're gonna need that positive 1. Okay. So that's the formula. Okay. Then all we need is to apply the formula now. Okay. So fx is a partial f over x, partial f over partial y. So what is my fx again? This is y minus x minus y, right? Yeah. So partial f over x, which give me negative 1. So negative negative becomes 1. Partial f over partial y, negative 1, negative negative, another 1. Okay. Yeah. So one of the common mistakes from last year is a lot of people mixed up the sign here. Yeah. So they put a negative, negative, or something like this, right? Yeah. Yeah. This is explicit. So when you have explicit means you have this specifically the expression for the z. That's explicit, right? So you look at the last line there. I said implicit. Basically, we put everything in a bracket, right? G of x, y, z equal to 0. So you don't have like a z equal to x squared plus y squared or z equal to 2xy, that kind of situation, right? So, or maybe it's a z squared equal to something. Yeah, 7. Yes. Yeah. So, but I think in last lecture I mentioned one thing, right? This is not n hat, right? This is not n hat. What we write here, the whole thing is n hat dA. If you remember n hat is this guy divided by the magnitude of this guy, actually, right? Yeah. Very good? Yeah. Yeah.
Can this be also expressed as an implicit one?
Come again?
Can this expression can it be also be expressed as an implicit one?
Can I build a?
Can they express the above equation in terms of implicit?
Yeah, this is a plane. I expressed this plane in the explicit format, right?
I can also do it in implicit way, right?
Or you mean also do it in implicit way, but this is already explicit, so you don't. Yeah, I guess if you apply the implicit formula at here, you probably will get the same thing. Yeah, so the implicit. Let's say you can argue it's a more general case of the explicit case. Yeah. So for sure, basically, you can consider, right? You can consider this whole chunk as 1 minus x minus y minus z equal to 0. So this whole chunk is g of x, y, right? You can consider that, yeah. But in this case, I think you would prefer this. Okay? As a matter of fact, we're not going to test the implicit, okay? Because in the class I didn't do any examples of the implicit. Okay? Yeah. So the formula is putting there just for the completeness. Okay. So we're ready for this surface integral now. Okay. So this dot this. Okay. And dotting product, negative x plus negative 2x minus negative 2x, and then plus z minus 1 dx dy. Okay, yeah. All right. So I'm not putting any limits at here yet. Okay, so this is the s here. So overall negative 3x plus z minus 1 dx dy. Okay, so now you have a z showing up at here, right? So you have to get rid of that, okay? Because you're integrating with respect to x and y. So how do I get rid of z? You get rid of z by looking at the surface S that you picked, okay? So the surface right now is which one? It's z equal to y minus x minus y. So we need to replace the z okay, with 1 minus x, 1 minus y, which is a surface S. Okay? So once you do that, you have negative 4x minus y dx dy, right? Yeah. So now at this step here, your next job is basically a double integral. A double integral, okay, with respect to this x and y. Limits for the x and y is based on the surface S. So surface S is in 3D, so limits of x, y is basically the shadow, right? Based on the shadow of the S in xy plane. Okay? So the shadow of the S in the xy plane is that triangle here, right? It's a triangle. So which direction you want to integrate, that's up to you, right? If you want to integrate dx, in my case set it here, then basically what we do is, right, we draw a line, right, in the direction positive x-axis. First contact 0, second contact is the line, that line over there. So it's 0 to 1 minus y. Okay, and the y will go from 0 to 1. Okay, yeah. So this is basically a very simple double integral, and can be easily calculated out, which is negative 6 over 5. All right, yeah. Okay. So those are basically typical approaches in terms of this Stokes theorem. There are a couple of more examples in the lecture. I'm not going to cover anymore. So take a look at the lecture notes for more examples, and also there's some additional exercise on the Connect. So I think everything has been uploaded on the Connect now. Okay, so I don't have any other resources or files, so it's all there. Same thing for 246. So you're ready to explore, to prepare, right? Okay. Yeah. Any questions? All good? Yeah. Yeah.
For you to be able to use Stokes theorem, does the vector field have to be conservative?
No.
Any vector field?
Any vector field, yes. As a matter of fact, that's a good point. What happens if the vector field is conservative? So what if the vector field is conservative? Yeah, it is 0, exactly. So if the vector field is conservative, then the del cross F will equal to the del cross F over here. That's a curl, right? The curl will be 0. Conservative field, that's how you check whether a field is conservative or not, right? Yeah. Okay. Okay, so I'm going to make use of the rest of the time to have a quick review at it here. Okay. So the review is review, so there's nothing new, and I'm trying to come up with a sort of good way of connecting all the dots at it here. Now, instead of writing lots of formulas at it here, right? Yeah, you have all the formula sheets, and you sort of have a knowledge point of what to do. So I'm going to give you a sort of overall structures at it here. Okay? Yeah. So number one is let's think about those fundamentals. Okay. Before we talk about the integrals, the surface or Stokes theorem. So think about all the fundamentals. Maybe the fundamentals, let's say, are trigonometry. Okay. And maybe it's a derivative. Okay. So I'll just list a couple of things that are here. Okay. And integral. Okay. So those are derivative integral of single variables. Okay. And then vector, okay, analysis. Okay. Yeah. So in vector analysis, there's a dot product and there's cross product, and there's some other properties, right? Yeah. So those are basically very fundamental stuff. Okay. So vector analysis, we used that a little bit. We actually did a little quick review at the beginning of the lecture, right? Okay. So then, based on this thing here, and we started to build up our knowledge. But I'll still call what I'm going to write at here. Still call them fundamentals. Okay. We'll still call them fundamentals. So just to remind me if I'm neglecting any fundamental things that you think not neglected here. Partial derivative. No, actually, before partial derivative, what did we have? Planes and lines in 3D. Right? Planes and lines 3D. Okay. Yeah. So each one of them, each one of them is based on something else, but they're more or less still kind of at the bottom of the food chain there. Okay. Yeah. So then we have a partial derivative. So now this is basically going into multivariable function, right? Multivariables. Okay. And we also have parametric equation of curves. So based on the parametric equation of the curve, and we have basically a couple of things, like for example, tangent vector, okay, or a unit or normal vector, okay, to the curve. You know, a couple of knowledge points there, right? What are formula? Just think about those things here. All right. So and then there's based on this partial derivative, those are not vector yet, and we have this gradient. Okay. So del f. Okay. So I'll still call this fundamental here. Okay. Yeah. Still call this basically this gradient more or less of one level up the food chain here, right? Because it's making use of a partial derivative. Okay. Yeah. So if you want, you can maybe draw a line over here. Yeah, maybe I'll draw a line here. Okay. So let's say gradient. Okay, del f. Okay. And beside the gradient of this one here, okay, we also have this directional derivative. Okay. Okay, directional derivative. So directional derivative not only just based on the partial derivative, it also based on the basically the gradient, right? Yeah. If you look at your formula, what's the formula of a directional derivative? You look at the formula there. There is a gradient f showing up in the formula, right? On the second lines of this page 1, right? Okay. So again, okay, those are relatively at the bottom of the food chain. Okay, so there's basically the fundamentals of what we're going to use. Okay. Yeah. Okay. So and then, okay, based on this one here, okay, I think if you recall that what happened next in our lecture is, okay, we started to talk about double integrals, okay, and the triple integrals. Okay, double integrals and triple integrals. And we also have basically applications, right? What are the applications? Okay, so for example, calculate the mass, calculate moment inertia, calculating center of the mass, right? Those are the applications of the double integral and the triple integral. Okay. So once we finish all of these things now that we went into a very important field called vector integral, right? Vector field integral. So integration inside the vector fields, right? Inside. So for that particular part, I think what we're going to use is basically it's this whole chunk here. Okay, it's this whole chunk. Yeah. Not necessarily everything, right? But it's basically all of this thing here is this, okay, providing the nutrient to the next of what we used, right? Yeah. Okay, so what we do is we have I would call, maybe I'll draw another circle here, but it's out of space now, right? So with the next topic is integral in vector fields. Okay. Yeah. So what's included, right? So include line integral. Okay, we have vector line integral, right? Vector line integral. Okay. And it includes surface integral, basically calculating flux. Okay. And based on the surface integral here and the line integral, okay, we have two theorem, okay, or three theorems. Let's see. One is Green's theorem, divergence theorem, and Stokes theorem. Okay, to connect those dots here. Okay, connect the dots. Okay. So there must be a better way of arranging all those branches here, but I guess it's not very precise. But it's more or less like that kind of flow here, right? Yeah. So essentially, okay, there are a couple of things, you know, between these branches here. For example, there's the concept of a conservative field, right? And there's this concept of path independence when you have a conservative field. Okay, so that's basically related to this line integral here. Okay, so the arrow probably should draw it up here. Okay, so conservative field. Okay, so line integral in conservative field. So, all right. Now, those are basically bigger pictures here, right? Those are bigger pictures. But in terms of specifically what happens, right, in each one of the topic, you know, that's essentially there are more details in it. Okay. So let's just say, for example, right, when we say surface integral, and you need to think about, right, different cases in terms of this surface integral. There's spherical, cylindrical, and let's say explicit. Okay, right. There's implicit. Okay, and there's another one. It's a parameterizing the surface within lecture notes that I didn't include here. Okay. Yeah. Okay. So overall, okay, based on this one here, you actually basically a couple of the knowledge point, essentially what I'm trying to say is, you know, after a few years, you probably will basically forget most of the part of the course. But usually, what I expect is you should still try to remember a couple of things that's very important here, which is basically what's del dot, what's del cross. Okay, yeah. So those three basically what we call the operators, right? Yeah, operators. So gradient, curl, divergence, right? So those basically things that you know, oh yeah, you know, in that multivariable calculus, I remember gradients, I remember curl, I remember divergence. What's gradient represent again? That represented the direction of greatest increase. The curl representing whether there's a circulation at a certain point, right? Divergence representing whether there is a source of sink or expansion or compression at that vector field. Okay, yeah. So exactly what formula it is, we'll look it up, right? So this is basically what I'm saying is, what you get off each one of the course, usually, okay, there are a couple of things that you should remember, okay, yeah, like that. You can brag about it to your kids. Not really. So, looking at everything at here, okay, I'm not going to go into details of each one of them now, okay. So I want you to basically looking at, okay, I'm providing a sort of a review of documents here. you can take a look at those details in the review documents. Okay, but I guess what I want you to look at this line of this diagram here is ask yourself what do you need to basically prepare, right? In terms of trigonometry, then the question is, okay, am I familiar with some of the typical trig identity, right? I mean, I provided you a couple of them over there, right? So I think that's what should be enough, right? Yeah. Again, technically speaking, you know, actually, only starting from last year, I gave a sign pi over 3, pi over 6, pi over 4 what they equal to, because I do find some students can write out the results of this one here. But in my opinion, you know, that should be part of this permanent memories in the brain. Okay? Yeah. So, as I said, the courses, the final exams are not accumulative. However, if you look at the way it goes here, particularly the last two, divergence theorem, Green theorem, Stokes theorem, as I said, you will have questions coming out of here, right? Yeah. So what do you need? You do need to know how to calculate partial derivatives, lines, planes, vector analysis, all of these things here, right? Yeah. So we won't have a dedicated question to, let's say, partial derivatives or lines or planes. However, if you feel necessary, you have to review. Parametric Christian curves, that's also necessary, right? So looking at the parametric of a circle or a cylinder, okay? And then how would you do the substitution, okay, when it comes to making use of that, right? Yeah. Okay. So anyway, it's a review. Usually, you know, I'm really bad at reviews, and I guess what I really want is I want you to look at basically what you think you need to get out of this one. You know, 1.5 hours to cover the whole course is not possible, right? Yeah. So next Monday, and we'll expect to use more or less as a question and answer type of session. All right. So I'm not going to talk anything new. Right. If you have questions regarding the last assignments, okay, so feel free to bring it up. And if you have questions regarding the additional exercise, also you can bring it here. Okay. Yeah. So I might just bring a couple questions just to go over here, but it's not mandatory. Okay. Yeah. So feel free to come. And any questions? All good? Yeah. So it's a little bit early. Yeah. And to give you a treat, I never finish my course early. You're damn late, so sorry for that. And so if you have questions next week, I'll be in my office. All right. So feel free to come.